Hello, my name is Gustavo Espinosa, and this is Physics 2212, Lab 3. Lab 3, Magnetic Field of a Bar Magnet, focuses on exploring the correlation between magnetic field and observable distances, on and off axis, and further understanding the Biot-Savart law, which relates the magnetic field with displacement and magnetic dipole moment. In this lab, we're going to download a magnetometer app on our phone and use the built-in magnetometer inside of our phones in order to record our data. The first step is to determine the direction of magnetic north. In order to do this, we lie the phone flat on a table and rotate until the x component equals 0 on the magnetometer app. We then set up the meter stick, orthogonal to north. And in order to locate the magnetometer of the phone, we slide the phone perpendicular to the meter stick in x and y directions, and mark axis with edges of tape. Finally, we move the phone at various distances along the meter stick, on axis and at a 45-degree angle, and record the magnetic field components into the provided spreadsheet. The main physical principle that we will be dealing with in this lab is the magnetic field, which is a function of the magnetic dipole moment, which moves from south to north pole on a magnet, and r, the observation vector, as expressed in the Biot-Savart law. Now, in order to better determine the relationship between the distance and the magnitude of the magnetic field, we will assume that all the values in the expression can be expressed as a constant k, leaving us with the equation the magnitude of the magnetic field, B bar, is equal to k times r to the n, where n is expected to be -3. Through this experiment, we will try to confirm this. Here are the collected measurements for the magnitude of the magnetic field at various distances r. Using this data, we are going to create a logarithmic plot of the natural log of b versus the natural log of r, which will create the following transformation, allowing us to use the linear regression and estimate the n value. Here is the linear regression shown, with the regression equation equal to -2.74 times x plus -14. These values directly correlate to the transformed expression above. As you can see, our n that we calculated is equal to -2.74, resulting in a margin of error of 8.7%, and our natural log of k is equal to -14. Now, in order to record the off-axis magnetic field measurement, we position the phone a distance of d perp in both the x and the y direction. In order to correct the y component, however, we must subtract the magnitude of the Earth's magnetic field from earlier. And using the same magnometer from before, we record the average magnitude of B. Here are the results of the off-axis magnetic field measurement data, with the average d perp being 0.183 meters, the average d being 0.2593 meters, and the average magnitude of B being 7.27 times 10 to the -6. Here is the computational model I created using Python. First, I found the magnitude and direction of the magnetic moment mu. Then, I created a function to find the magnetic field, which takes in two arguments, mu and r. It first finds the magnitude and direction of r, and then uses the Biot-Savart law in order to return the magnetic field. After that, I created 6 vectors for the observation locations, 2 which are on axis and 4 perpendicular to the axis. Then I created 6 arrows to represent each observation location, which I created in the last slide. Finally, I created an arrow to represent the magnetic field 45 degrees from the axis. Here is the output of the code that I created. As you can see, the orange arrows represent the magnetic field on axis, the cyan arrows represent the magnetic field perpendicular to the axis, and the pink arrow represents the field 45 degrees to the axis. As you can see, the net magnetic field of the computational model is a little smaller than the net magnetic field found in the experiment. This can be as a result of human error or small magnetic fields in the surrounding area when doing the experiment. If I hadn't oriented my experiment to compensate for the magnetic north of the Earth, and instead laid out the meter stick at some intermediate angle, all observations that I had would be affected by the Earth's magnetic field. The x component found using the magnetometer would be non-zero, and you would not be able to use it in order to measure the magnetic field that is normal to that of the Earth. Therefore, the values of mu, k, and n would not be accurate. If I were to stick two identical magnets together, end to end, I would expect the magnitude of the magnetic field found to approximately double due to the superposition principle.